Hello everyone, let's solve our next problem. So this problem comes from a viewer. It was sent to me by email, and it's said to come from Stewart's calculus textbook. It's also accompanied with a figure containing a whole bunch of circles. So the question says, the figure shows two circles, C and D of radius 1, that touch at P. The line T is a common tangent line. C1 is a circle that touches C, D, and T. C2 is a circle that touches C, D, and C1. C3 is a circle that touches C, D, and C2. This procedure can be continued indefinitely and produces an infinite sequence of circles Cn. Find an expression for the diameter dn of Cn, and thus provide another geometric demonstration of example 8. Okay, so I don't have details of what this example 8 is, but really, ultimately what we're asked to do here is find an expression for the diameter of all these circles. So basically we have a sequence of circles which are kind of constructed recursively, and we want to find the diameter of any arbitrary one. I will recreate the diagram that I'm given. This will require me to draw a couple of circles. Hopefully I can do this without too much difficulty. So this is sort of what the initial part of the diagram looks like. I have two circles. They both have a radius of 1. This line down here, no thank you. This line down here is tangent to both of the circles. And then I have a whole bunch of smaller circles created like this. So this first one, bad drawing, but whatever. I hope you get the idea. It's tangent to each of the individual circles intersecting at those points and tangent to the line there. And then we have circles built up like this. And we'd like to find the radius or the diameter of each of these circles. So we'll call that D1, D2, that'll be D3, and so on. So what might be the best way to do this? My first instinct here is to look at the first circle, this one here, maybe connect the center of this circle to the centers of the two others, and try and write down an expression that the radius or the diameter of that circle has to satisfy. I think I'm going to start like that, and then I wonder if, like, that might work, that might help find the diameter of the first circle if we draw that line there, maybe drawing this line here, drop down to the line to this tangent line. But then finding the diameter of the second circle, I wonder if we're going to have to use the diameter of the first circle in some kind of expression. Anyway, I'm not 100% sure what's going to happen on this, but I'm going to redraw the figure with only the first circle and only kind of the parts of it that are necessary, so that I can draw something a little bit bigger. Okay, so drawing the figure like this, basically what I have written here, this algebraic expression, this is just the Pythagorean theorem applied to that triangle there. We know that each of the larger circles has a radius of 1, and so this length is 1, And with the center of this circle here marked off, this is of course a radius. And so this length is 1 minus r, or I'll call it r1 because this is the first circle. This distance here is 1, and the length of this segment is 1 plus r1. So here I just have the Pythagorean theorem written down for that triangle, and I should be able to solve for r1 pretty easily from this. All right, so the first diameter is d1. Now let's think about how I might find the second diameter. I'm just going to reuse this diagram and erase some of the labeled distances here. Let me put in the second circle. So I don't know for sure if this is going to work, but let's give it a shot. This length here is again 1. This length here is 1 plus the radius of my next circle. I'll call that radius R2. And this length is going to be the first diameter plus the second radius, or 2 times the first radius plus 1 times the second radius, right? It's just that distance there. And so I can also write down the length of that line. So let me write this out here. This is 1 minus R, no. 1 minus 2r1 minus r2. And so I have 1 plus r2 squared is equal to 1 minus 2r1 minus r2 squared plus 1. Now, of course, I know what this quantity is, but I want to think ahead now to generalizing this procedure. I should be able to generalize this procedure quite easily, except that as I keep building more and more circles here, this thing is going to always be of the form 1 minus the sum of all of the previous diameters minus the radius of the current circle we're interested in. So what is and it would be nice to have a general expression for that in some way. Let me think. You know what here's what I'll do is I'll expand this. Or I'll even write out the general relation that I'll need. 1 plus rn squared is equal to 1 minus 2 times the sum of rk. K goes from 1 to n minus 1 minus rn squared plus 1. And I guess I'll just want to try and keep that as some kind of general term. So what will this do? This will give me a relation between Rn. When I expand this and solve for Rn, it'll give me Rn in terms of all of the previous radii. So I can write Rn in terms of this sum of other terms, but it doesn't really give us a nice so what I think I'll do now is I'll write out explicitly the first. Let me solve for Rn and then write out the first few values of Rn and see if I can figure out a pattern of some sort. Oh, a 1 cancels as well on both sides of the equation, right? And all of these things, yeah, I'm writing everything in terms of R instead of D. I'm seeing now that using the diameter would have been more convenient because a lot of factors of 2 will just disappear, but that doesn't really matter, right? Oh, I have something nice that cancels on the left. Let me expand the left completely. And now I'll expand the right because I see there's going to be more cancellation. I must have a mistake somewhere. Yeah. There's an Rn here. So some of my algebra here is wrong. Well, I can still write this. There was no sense in expanding that right-hand side, though, so let's just undo that. Okay, so this is the diameter of circle N, and I've written it in terms of the sum of all the radii of previous circles. So I'm going to now manually compute the first few values of Rn. So R1 was given, and in fact we see that when n is equal to 1, both of these sums are empty sums, and so they are equal to 0. And I see that I just get R1 is equal to 1 over 4. So our formula here coincides with the direct expression we had there. Let's compute R2, or in fact D2. So there's D2. Maybe I should make like a table. So R2 is going to be 1 over 12. D2 is 1 over 6. Sigma n is R1 plus R2. 1 minus 2 sigma 2 squared divided by 4 times 1 minus sigma 2. So there's R3 and D3. R3 is 1 over 24. D3 is 1 over 12. And okay, what is sigma 3? It's going to be 1 over 3 plus 1 over 24. Okay, so what is this number on the bottom? 40. R4 is 1 over 40. Okay, I'm not going to compute the sigma 4 yet. So the pattern that I want to point out here, and in fact, the viewer that sent this question, it has the correct answer highlighted. So I knew already to look for this pattern. But if we look at the diameters, D1 is equal to 1 over 2. D2 is equal to 1 over 6. D3 is equal to 1 over 12. D4 is equal to 1 over 20. pattern here is dn is equal to 1 over n times n plus 1. So this is 1 times 2, this is 2 times 3, 3 times 4, 4 times 5, and so on. So we see that this certainly holds at least for the first 4 circles. If I wanted to show this in general, I would probably go by induction. So we'll assume dn is equal to 1 over n times n plus 1. And we want to prove that dn plus 1 is equal to 1 over n plus 1 times n plus 2. And I'll use the relation that I derived earlier between dn and sigma n minus 1. But I suppose I would also have to, like, there's a pattern in the sigmas as well that I think I see something happening with sigma also. I'm not sure exactly. Oh, you know what? Yeah, okay, so dn is 1 over n times n plus 1. I want to write this as a over n plus b over n plus 1. So we're basically doing a partial fractions type thing here, because I think the sigma, the sum of the radii, we should be able to write it as a telescoping series. I should be able to just, hopefully I should be able to just identify exactly what these things are, right? It'll be something like 1 over n minus 1 over n plus 1. Okay, so here's how we're going to do this. We are going to do this by induction, ultimately. We're going to assume this. We're going to prove this. So in each case, this is equivalent to 1 over n minus 1 over n plus 1. And this is equal to 1 over n plus 1 minus 1 over n plus 2. I also have sigma n minus 1. This is defined as k. The sum is k goes from 1 to n minus 1 of rk. Which is a half of the same thing when you put the diameters in there. So dn plus 1 from the relation that I derived up earlier, it's basically exactly this here. I've got some index problems here. I need to put a plus 1 there. I need to get rid of the minus 1 there because we're doing the induction step. Okay, so sigma n with this telescoping sum is equal to 1 minus 1 over n plus 1, which is n plus 1 minus 1 divided by n plus 1. N over n plus 1. Okay, so now I have a straight formula for dn plus 1. Oh, missing a factor of 2 again. Jeez. Well, no, I have this thing here is not written in terms of the sigma subscript n. It's written directly in terms of the sum, so I can do the substitution here. All right. Sorry, I'm just confusing myself with what my notation convention is. There we go. So that's the induction step done. We did check the base case. That's one of the first things we did. So this is proven now. So what were the key steps in this? Well, using the diagram and identifying this Pythagorean relation that allowed us to relate each new radius to all the previous radii, that was one key for sure. But then we ended up getting an expression for each radius in terms of the sum of the previous radii, which on its own, okay, that's a good step. That's nice. But if you don't know the pattern already in if you don't know the pattern in the diameters or the radii already, it might be difficult to figure out what the general expression for this thing is. I think if I hadn't been given the answer by the viewer, essentially, in the submission, I would have probably continued this pattern a little bit more and hopefully seen that the denominator of dn is just n times n plus 1. And then I know that an expression like 1 divided by n times n plus 1, it's a common expression to see partial fractions applied to. And so the combination of partial fractions and knowing that I need to compute a sum of these terms, I just kind of, with experience, I've seen this happen a lot with the telescoping series come out. And so computing this sigma n minus 1 wasn't too difficult. And then it's just a question of, once you recognize this pattern, proving it. In this case, I used induction, proving that this thing holds for all values of n. There might be a nicer way of doing this. Maybe the geometry lends itself to a nicer way of directly getting Rn in terms of something rather than using all the previous radii, but I don't see that, and I don't think it would be the easiest thing to work out. I'm not really sure. Yeah, I just kind of picked away at this problem one step at a time. I did not see the overall trajectory of the solution until about partway through this recording. Just picking away at, figuring out the first radius, and then seeing that process would generalize and relate each radius to all the previous radii. Yeah, it all just kind of worked. But it would be cool to see if there's a direct way of doing this rather than like this recursive way of doing it. If I have any more to say about this question, I'll put it down in the description. Otherwise, thanks for watching.